the domain of Industry 4.0. In the recent past 5 years, 6 years back, we just started at NIFT working in the domain of Industry 4.0. We also enable the courses in this domain at our UG level as well as the PG level. I am taking care of the couple of the subjects like mechatronics, Internet of the Things, additive manufacturing at NIFT. And along with my research team, and one of my students is also present here, Rajan, working in this domain, and we're trying to identify the solutions which are low cost and have a good implementation in the area of the apparel manufacturing industry. So today's my focus of the Industry 4.0 domain is in the area of the apparel manufacturing industry. Because we as an NIFT catering apparel manufacturing industry, and we try to build the application in that domain, but that's not the limit. That will give you a fair idea what are the architecture of a Industry 4.0 application can be possible, and they say and these products or these projects are very scalable to other manufacturing industries also. So not wasting much of the time, I'll just start with the presentation. My presentation is structured in a manner that I just talk about the Industry 4.0 in 3-4 slides, and then directly come to my projects, our project which we are working on. And I try to cover the 4 of the projects which we are working at NIFT. 2 are commercialized projects which we have developed in recent years, and now they're ready for the industry. And we have a couple of the orders, and the industry is implementing those projects in their industry on the shop floor, and 2 are in the research phase. So I'll also try to share what challenges we'll face, how we'll able to identify those are the requirement of the industry. So just starting with that, my presentation. As everybody knows, we are in the era of the Industry 4.0. It's a 4th industrial revolution, and just to reach this place, we have passed through in a long distance, starting from 1780s. Till that time, the evidences were there, the humans were working with their hands, and the machine was not in the role of the manufacturing. But at that time, some participant is raising hand. Should I need to answer that?
No, you may continue. If there is a question, they'll put up in the chat box.
Okay, fair. So at the time when initially the power generation started, and the initial literature says the water and the steam was the initial where the power generation started, and the first production started into the apparel only, not the apparel. Basically, it's a textile. And looms were the areas or the machine parts with textile industry, where this first industrial revolution started. And later, in the age of the 1817 to 1950, when electricity was invented, the mass production started, because that time we got a flexibility that the power can be generated at one place, and it can be transmitted to another places, and that helped us to do the mass production, and we have the better efficiency with the electrical motors and other things. Later, we have a computer into the place, and we have control theories, and the assembly line systems are there, which can be automatically controlled. Automation was into the was the one of the bigger aspect of the manufacturing, and a system independently can be do the automatic manufacturing, can be converted into the automatic manufacturing process, and that was the time of the automation. But till the time till 2000, the technology was not that much developed that we have a physical or the commercial solution for the whole line assembly, which are integrated with each other. But later, with the technology advancements, specifically in the domain of the computational power, sensor technologies and other tools, we were capable to integrate the automation from initial to end point. And that whole integration happened because of the sensors and computational power. Later, various terms comes into the picture, like an edge computing, cloud computing, AI, big data. Those are the part of those systems. But what we can say, because of the computational power increases, we can say we are in the time frame of the cyber physical system, where whole system can be integrated. What is happening on one system that gives that can give a feedback to the next stage, and we can control the machine at the that the remote places also, and there is no human being intervention. Machine or things talk to each other. That is the basis of Internet of the things, and that whole possible. So now we are in that age. Now, smart manufacturing and Industry 4.0 are the synonym to each other. There are various definitions here. Just mentioned a couple of the commercial definition which industry understand, and this around is a German term, Industry 4.0, and smart manufacturing is on the top of that. What the smart manufacturing? It is basically a broad concept which is not an individualistic solution, individualistic technology which we implement in one of the section of an industry and we'll say that my industry has become the smart industry. It's actually the implementation of the various tools, various solution in combination of the various technology and solution, which collectively, if implemented in a manufacturing ecosystem, so we have a smart manufacturing. That's the definition. Now, just to work around or just to understand the ecosystem of a smart manufacturing, there's certain pillars are there, and those pillars are built on the base technologies like IoT, Internet of the Things. We have a big data, like every sensor, every action, industry is creating the data. Now we are trying to get a meaningful output from those data, and those are not like in a localized data. They can be transmitted to at the various places at the cloud space, and we have a good analytical tools available, good computational powers, and AI is the part of that. We can take the intelligence decision. So those are the base technologies, and on the top of that we have nowadays cobots, the robots which can work with the human beings. Those are called the cobots. We have a technology like 3D printing, we have an AI, we have an augmented reality, we have a cyber physical system, and these whole in totality and in an integrated manner just conclude a basis of a smart factory. Now, smart factory, there's not one specific definition I can put, and I can say this is a smart factory, this is not a smart factory. There's the various steps of reaching at the smart factory. We are not getting into those, how we can achieving the smart factory concept, but there are the audits are there. There are the various the service provider which can assess your company and tell you what level of the smart factory you're working, what are the possible path you need to take up, what are the various sector in your company you need to concentrate, and you can do the various solution and you can move to the next level of the smart factory. Now, I'm just describing the ecosystem in the apparel manufacturing industry of a smart factory or Industry 4.0. Apparel manufacturing industry is basically a three-stage manufacturing process. We have a fabric with us. We try to cut the fabric, then we have to sew the fabric, then we have finishing the fabric. So these three are the basic department. And the sewing is the most important and where the maximum value addition happens. That is the sewing department. We have the general process in the apparel manufacturing industry. They more or less across the companies are the same. Like in every manufacturing company, we have a workforce which need to be go under the various training just to attain the required skill set which are required for the various operation which are the part of your manufacturing process. We need to do the planning for the workforce. We need to manage them. So that one of the aspect we do, and that across the department we need to do. Now we also need to do the production planning and control. That's another area, as we can say as a general process. We also need to do the industrial engineering. We have to do the inventory management. We have to do the quality control. The quality control definition overall is the same, but the various requirements are different for the quality control. That again, the product specific, industry specific. We also need to do the machine maintenance. So this is not the exhaustive list. This is the majorly cover task or the the activity or process we'll do in an industry. Now, now we are trying to understand these all things with the domain of the value drivers. Like if I need to do the workforce training, so what I need to do? I need to do the virtualization of that. How I'm going to do the workforce training? What are the skill set required for my various tasks? And whether my available operator workforce are skillful in those tasks or not. What is their present skill set? Where is the gap? So those things are required to be identified. So that's, we need to virtualize those things. We have similarly, if we need to do the production planning and control, we have a vertical integration. Now, vertical integration means that what is happening into the cutting department, what is happening into the sewing department, what is happening into finishing department. We have to link all those things. How we can link all those things? That can be done with the help of the various sensors. Wherever we need to do the vertical integration, what are the tools which help us to do the integration vertically? So we require the sensors because they can give the data from the various location. Whatever the data information we're getting through the sensors, we need to convert them into the meaningful aspect. So their analytics comes, and just to transmit those sensor data to the cloud, we need the Internet of the Things, we need the transmission buses, and just to store them at the cloud, so we need a cloud space. Analytical skills are required to make a meaningful things, just to reverse back what we did as an intelligent solution, what thing we need to implement back to the implement back on the the shop floor. We require the actuators. So these all are the part of the industry 4.0. So similar manner, we can see the virtualization, also virtual commissioning, simulation of the process. We also need the AI for the production planning, automation. We require the machine-to-machine interface. We need the cobots. We need the automatic guided vehicles. Traceability is also required. That specifically for the inventory management. We need to understand where is my inventory is lying, where is the bottleneck, what is the lead time of the various product. For the flexibility, like technology, additive manufacturing can play in a good role. For the energy management, we have an energy efficient monitoring system. Those are also the IoT enabled systems. They can give the data, what energy consumption we have. We have the various various big companies nowadays working in the area of the compressed air utilization, specifically automation industries and all. So that compressed air, which sometimes costs us more than the electricity, because that generation wastage, and also just to understand how much we are generating, whether that is utilized at the appropriate places or not, how we can reduce and how we can make use them in more efficient manner. So we require the what is happening on the shop floor, what is the total generation, what is the consumption rate at the various places. So to understand that, we require to put the sensor on the places, so they'll tell us in the real-time scenario what is the compressed air consumption ratio at the various. So we can build the application based on that. Now, and just coming to the mega trends in the apparel manufacturing industry, which is related to the industry 4.0. There are so many applications we can see in the apparel manufacturing industry using the one of the tool, AI or the big data. I mean, those have a good application into the retail also. You have seen in day-to-day life example, there are a couple of the websites or the app you can see. You click at some image on some dress, it will give you you might use a Google Lens in your mobile also. You can click on any of the dress and it search the similar dress or similar suit on the web-based platforms, and which are closely to that type of the dress, and they will link you with the various Amazon, Myntra, and other platform where those garments or those dresses are sell by the manufacturers, and you can directly have an access of this. So there, these works on the AI and the big data. We have a quality on the shop floor also. What is the fabric quality, measurement of the various garments. So there AI can play in a good roles, and these are the mega trends where the researchers and commercial solutions are developed by the industries and the service providers. Now, robots and cobots have a fabric pick and place, fabric manipulation during sewing. So I'll just play one or two video for just to make you understand what application I'm talking about. Simulation also have into the physical, psychological, physiopsychological parameters. They're the recent there's a recent research has been done in Hugo Boss and one or two companies also that where what is the mental health of an operator in day-to-day life when he's working on the shop floor, that has been measured, and those deviation into the mental health, like if he's having the high BP, is having not a good mood, so that affect their production also. So those type of the studies has been done. So those done on the simulation platform. And for the fabric to the garment, we have a various simulation softwares. Those help us to convert the fabric into the garments. Industrial IoT have an application into the predictive maintenance, just to network the various sewing machines. So there we have an industrial IoT. Digital twin is just a simulation or just to understand what actually happening on the shop floor, and we have a real-time scenario, or we can do the simulation on that. So this is new terms, digital twin. So that have an application into the intelligent skill mapping of the operator, and 3D printing having into the apparels manufacturing also, and as well as the sewing machine parts manufacturing at the point of consumption. AR also have a maintenance and the garment measurement. So these are the buzz, or these are the tools of the industry 4.0, which have an application, and across the globe people are working in this domain. Now I just play 4 videos parallelly here just to make you understand what is happening in apparel manufacturing industry. Like this is a robotic arm. This is used to place top layer of the fabric. This is a pocket. We need to understand the picking off on a fabric top layer is not easy like we're picking off a metal piece, because when we use the vacuum, so it can the fabric is porous in nature, and the vacuum will not help. You can have a couple of the stack can be picked up simultaneously. So electrostatic charge can be one of the option. And here you can see that just it's only picking the one top stack only. The next one, you can see the robots are there in apparel manufacturing industry. This is a universal robotic arm. This is one of the leading apparel manufacturing in India. More than 70 factories they are holding. And this cobot is doing the pressing and the steam pressing here. And you can see it's doing very efficiently. It reduced the total manpower requirement. And this third one is the the autism vision-based solution. You can see here the camera is mounted, and without the human intervention, this is the most difficult operation in the apparel manufacturing industry, where the one concave and convex surfaces are required to join, and this can be here it has been done without the human intervention. And there's a last not the least one here. We have a software company where the whole garment, this is the Adidas design, and they're stitching the whole t-shirt without the human intervention, and this platform is patented by them. It's a pneumatic system which moves the garment or WIP, work in the process garment, at the various locations, and that will automatically stitch, and we have the final product in front of us. So these are some of the smart factory solutions which can be implemented on the shop floor, and they can lead us to the apparel smart industry 4.0, specifically apparel manufacturing industry. Now, specifically at NIFT, we are also working in some of the contributing to some of the mega trends in this domain. And the red one, we are the areas where we're presently working, and out of these 4, I'm going to present today. This defect prediction and measurement inspection. So demonstrate this defect prediction in a garment. And then we have which is based on the AI, and we also demonstrate the intelligent skill mapping of a sewing operator. What is the skill set inherent in a sewing operator? What is the present way of evaluating that, and what we are proposing here. This is a commercial solution we are proposing to industry. And 3D printing, manufacturing, or what you say, the fabrication of the 3D printing parts at the point of the consumption, we are working in that domain. So these I'm going to demonstrate. So coming directly to the these 4 projects, intelligent skill metrics, and also the intelligent production monitoring, 3D printing machine parts, and intelligent fabric inspection system. So I'll start with the intelligence skill metrics iSmart, and the commercial name is the iSmart for this. Now, skill metrics is the one thing. Like before talking about the skill metrics, why it is required. Now, in a garment, any garment, like we have in a T-shirt, we are right now. I'm just wearing this formal shirt. It happens in the assembling line system. It's having a collar, it's on a front placket, it's on a cuff, it's on the side seams, it's on this shoulder to the arm attachment. So these are the various operations which are required to be stitched by the various sewing machine operators. Now, how we in present scenario evaluate a skill metrics of an operator? So we have an ABCD ranking in apparel manufacturing industry, and A class operator is called as who is capable to do the multiple operations. So these skill set is based on the what operation they can perform, not what the inherent capabilities of an operator to a what you say the type of the sewing. So that is not there in the industry. So I'll just play a video here for you. Like this is a very basic way to demonstrate the skill set. Now here you can see in this video what is happening. This is an operator who is attaching in a what is the pocket on a formal shirt. Now you can see he need to move in one direction straight, then he need to take a right turn or left turn, then he need to move another direction. So straight line with a short burst is the type of the skill or type of the operation, type of the sewing required here. But industry says whether an operator is having a capacity or skill available, he can capable to do the pocket attachment. But that is the base on the whether an operator is capable to do the straight stitching with a short burst. So that is missing area which identified in the industry. And what the general way of the evaluating the skill of an operator in an apparel manufacturing industry, they give them an operation like this. They do the PMTS time study, how much time he takes, and whatever he stitch, they just see by the naked eyes, and they tell now it's acceptable, it is not acceptable, and whatever the time he takes, whatever the time he takes, so they say like is a good operator or the bad operator. But these things are subjective in nature, because when I am evaluating as a quality, whatever an operator is stitching, and some another evaluator is evaluating the same operation, he have a difference of opinions. One says is a good, another one says now he's close to good, he's not a very good operator. That much margin is there, and the same that's why it's a subjective in nature. And understanding the PMTS time study, that does not serve the purpose in total. Like we can give many of time an example, like we have 2 car drivers, they are required to drive from Delhi to Ahmedabad. They have started from Delhi at the same time. They reach in the same time also. It doesn't mean that both are the good drivers. It also depends upon how they're driving the vehicle, like whether they are accelerating more, whether they throttle more, whether they retard more, whether they put the brakes more, how they're taking the curves and all those things. That is missing in the present way of the skill evaluation. So there we find an opportunity, and just to evaluate that, we understand what are the various parameters required to be evaluated. So we came up with a solution. So it is an human-less intervention. There's no human intervention required to evaluate in a skill set on an operator. So we develop an encoder. This is a black box you can see, which is mounted on a sewing machine, which can be mounted to any of the sewing machine. It captures certain parameters of an operator while he's doing the sewing, and we developed the algorithm to using this data, and we evaluated them on the 8 parameters. What is the average speed of the operator while he is performing the task? What is the total time he elapsed? How many times he starts? How many times he stops? When did he work with the same speed, acceleration, and all? This is this is also, I would like to mention that this is also the NIFT patented solution. And what all things we require, this encoder can be mounted on a machine, and we have an input to a laptop where we have a proprietary software which is capable to capture the data, and we have made a system at the cloud the data will be uploaded on the cloud once he's done with the whole testing, and whatever he tested, that need to be scanned on a flatbed scanner. I'll just show in a video for that how this whole process works. So this is the human machine interface HMI and the encoder here. This can be mounting on the sewing machine, and you can see we have a desktop app here, and this my encoder or this black box can be attached to the laptop. And here what we need to do, we need to put the certain user management data, like which work order while we are doing. So this as a commercial solution, so we are showing like this. So here we can see the list of the operators which are available into the database. We have another section where we can add the operators. So I'm giving a template to an operator to stitch. I'm doing the barcode also. So this is the interface, and this is the barcode print that specific code what test is going to perform, and this is the template the operator need to stitch, and the barcode need to be placed over here only. Now operator is given to test this. He just press the start button and he'll do the stitching in the industry. Now once he's done with the stitching on these red lines, he need to use the black thread to stitch over the red lines. When he complete with the stitches, so he just press the end button, and the in between data has been stored into the local machine, and then the evaluator just need to upload the data on the cloud server. That's the only thing you need to do. Now just fast forward this. Now once he done, he's press this end button, and this need to be scanned. Why we are doing the scanning here? Because he or she need to stitch on the red lines, and he is using the black thread. So we have a dedicated algorithm which able to identify how much deviation has been done on the red to black. So wherever there is a deviation at the pixel level, so my algorithm will able to understand that. I'll show you how this works in the backend also. Just give me a second. Okay. Now here you can see, I'll just we'll do one of the companies data, like Raymond Shahi. Okay, I'll go with the Shahi here. Various operators has been tested using this. Now this is one of the operator here, like this Sunil Kumar is even given the various test. Shahi, this test ID is this. Now he was supposed to stitch this template. This is the image template, and he stitched like this. On the screen you can see this was the template given to him, and the data was calculated, and this was the actual he stitch. So you can see he used the red black thread to stitch on the red lines, and it will take a bit time. Okay. So this is the data we captured through the encoder. This is for the process evaluation, and this one is for the quality evaluation. So now for the each operator we have two scores. One is the quality, how much he deviated, and what is the process he attained. So like you can see, if I drag the box here, you can see here. So this is just for the demonstration purpose. These all things we can calculate at the back end. We can generate the reports also, and you can see in the upper half he is having the good quality score. On the lower, where you can see that he's missed some of the red lines, so the quality score is less. Okay. So using this, we also develop the different type of template through which we are able to understand what type of the skill set is needed. Here you can see in this template he is the short burst and the sharp turn. So this somehow resembles to the operation of the pocket stitch. So we have a different template here. You can see the another template is there, another template just to fold and place. So we developed the 5 different template, and based on that we are capable to understand or evaluate the skill set of an operator. Sorry. Now I'm just showing you what type of the data we are able to evaluate. Here you can see for the individual operator, we can have an overall process score and the quality score. Along with that, we have 10 skill attributes, like the suitability of that operator with the curvature swing is the 44.95%. So these type of the reports we can generate for the individual operator, and using this QR code across the globe, you can see whether this report is authenticated or not. That can be checked from this portal. And at the company level, we are able to generate for reports for individual operator like this Anita Devi, how she's been evaluated on the 10 different parameters, like here, and the green is the good. We can also have an absolute scale of the operator. This is a 77 operator data. You can see here, that is what is their standard across the globe. So red is the worst, yellow is the medium, and the green is the top one. So you can see for this company, only for this pivoted anti-clockwise type of the skill set, there is no operator in the world-class bench level. So this is the absolute scale. Here for the relative scale, we can say within the company, what is the distribution of the operator for the various skill sets. So that's where you can see the, just like in a normal distribution, it's close to the medium. The average guys are almost have the highest value, and the poor and the best are the. So this was the iSmart we have developed. What advantage we have? This is the first operation neutral skill evaluation system in apparel manufacturing system. It is supported by the PMTs of the method time measurement. It's 100% objective. It's no human intervention required. It's a easy yet secure approach to skill score of the SMO, stands for sewing machine operators, through portal, enabling easy portability. Like one operator move from one industry to another industry. So we have a what is it, a database, or it's a type of the resume they can carry with them to move from one industry to another industry. No special hardware, software required, and perfect for the production manufacturer. They also can what other advantage can have of this type of the solution when the new garments comes. What are the type of the skill set required? They are know what skill set they are having with them, and based on that they can do the training of their existing workmanship. Now the next project I'm just would like to share with you is the intelligent fabric inspection system. Now what happened in a apparel manufacturing industry or in a textile industry, the garment we are having, they comes from the textile industry, and they can have a various defect in them, like sometimes they can have a hole, they can have a stain, they can have a slurp. So there's 18-19 different type of the defects can be possible. And what is the general process in an industry to identify those defects? So I just play this video, and this is also one of our project. Now, current fabric inspection process, like we just have meet Babita. She's a fabric inspector. What she is doing, this is the roll is coming from this side to this side. She's standing in front of this roll and just trying to identify where is the defect, and wherever she finds a defect, she stop the machine and put a sticker over there and put the record in her sheet. So this is very time-consuming, monotonous, very fatigue-oriented, and the efficiency of the operator goes down from starting morning to evening. And what challenges she is facing? She is time-consuming. The present level of the working is 15 to 20 meter fabric inspection per minute, and the various distraction are there, like cognitive distraction, surrounding noise, and the videos also put in a distraction, fatigue also. So those are the issues which the fabric inspector faces in day-to-day life while doing. And what the general accuracy, she is able to identify 65 to 70%. So these are there in the literature that if there are 100 defects, an operator is experienced operator, we are talking about, is capable to identify 65 to 70. Now, sorry. So what we thought of with the development of the vision technology, why can't we just automate with the intelligent solution? So we thought the human being can be replaced by an AI-based solution. And what will be the future way of inspection? It will be the faster, it will be more accurate, and it will be consistently and very repeatable, 24/7 operational. How we are going to implement? So the human being will be replaced by the cameras. These are the industrial grade camera. I have just shown the DSLR camera, but that will not work. So we'll working on the industrial grade camera, either with the the Basler or the Cognex company cameras, and those will capture the image. They will go to the processing unit. An AI based solution will able to identify what type of the defect is and where it is exactly lying. So we work on this, and we just started into the research domain. So we started with the solid garments, which is of the single color, and these are the 4 defects we initially identify, which contribute 60 to 70% of the total defects in volume. So we took them as in a first pilot run, and these are defect. These are called as a knot, slub, hole, and the stain. We took the solid fabric, and we developed on the MATLAB platforms, and we identify the various AI based through the transfer learning. We'll use the VGG16 as an the AI model. Tools which are developed, so which are able to classify I think more than 1,000, or AICTE is also there, which is capable to identify the various 1,000 different objects. So we did the transfer learning. We got the 5,000 images from the industry images. Literature also talks about that the people have achieved a good accuracy, but no literature supports that they use the industrial images or industrial pick to develop the models. So what accuracy will get 95 to 97. So we not only doing the classification here, we are also doing the object detection, like where exactly defect is there in object. So it is 100% repeatable. So I would like to live demonstrate this. So I request Rajan, what we have done, just to show you. Rajan, are you there?
Yes, sir, I'm there.
Yeah, so you need to present your screen and show the audience like how it is exactly working in the live scenario.
Yeah, I'll do it.
Okay. Here
Is
you.
it visible?
Sorry, Rajan, please continue. Sorry.
Sir, continue. I was just asking if it's visible or not.
Yeah, screen. I think the screen is visible. I can see the screen. Now you can see that this is the live garment he is having in his screen in front of him, and he just deployed this code here. You can see that there's a bounding box. It talks about where the type of the defect is exactly here. Now that was the slub. Now knot is there. This is the bounding box here. You can see which tells where the knot is there. So we can also able to identify the coordinate of the defect on the garment itself. Here you can see multiple defects are there. Stain are there, 2 stains are there. So the system is intelligent enough; it's able to identify where the 2 stains and where they exactly lies in that garment. Next. So this is the another stain you can see, and it makes in a bounding box. Thank you, Rajan. And this is in a hole. You can see the system is intelligent enough to identify the hole. So you can see this is the hole. It makes the boundary out of the box. Thank you, Rajan. Thank you very much.
Okay.
Now, we also developed the able to deploy the code on the mobile also, and on the MATLAB platform. So we are just showing the very fast and through a video how it can be done on a mobile. A MATLAB has been implemented as a small app which can be. So we should have a credential to log in into the MATLAB mobile app. So that's there, and then what we use, we allow all the sensors to be used by the this MATLAB. So sensors are there in a mobile is the camera, which we are going to use. Now this is the code we have written, and this is the outcome of the long-term training. We are not going into detail how those things have been developed. Now I'm just demonstrating the application part here. Now if you take the picture, it's evaluating here, and it will tell you in a while. Just so it comes evaluated and tells that it's a whole, and 85 with the 85.7% confidence level, it's telling us in a whole. So that's the application is deployed. Now we are working with a company to deploy on the real-time scenario. So we are in a phase of identifying the cameras which can be mounted on the machines, how the live feed can be go to the processing unit, and whatever we have developed, it will able to identify where those 4 defects are there. And we are also making a platform for the unknown defects. The operator will teach it like this is the defect, and those will be used to further train. So in the next 1.5 years, we should have a commercial solution with us. So we are in that phase. Yeah. Next, we have an additive manufacturing, which we are also one of the industry 4.0 tool, and we are using it to develop the solution for the apparel manufacturing industry, specifically for the spare parts and the type of the.
Deepak, sorry to interrupt you.
Yeah.
This presentation is not visible on full screen.
Okay. Just give me a second. Sorry. Now it's visible?
Yes, visible now.
Yes, sir, it is visible.
Okay. So why 3D printing? Because at the again, the basic thought process was just to develop the low-cost manufacturing solution specifically for the spare parts of the which are used into the machines at the manufacturing sites. And as the characteristics of a 3D printing is always be used when we are having a high variability and low consumption rate. So you can see here the very different type of the zigs and fixture type of the things we have in a folders and attachment. Those are required to guide the fabric doing the sewing operations, and a company can't afford to have all types of these attachment and folders. So they just, because that increase their inventory costs, and they also required once in a blue moon. So what we thought, why can't we manufacture them at the point of the consumption? We have a digital data with us, and whenever needed, we can print at the point of consumption. So that cuts short the lead times also. So we can develop the indigenous solution. We can have a customization. Like I just like to give the same example. This is the placket where the buttons are there, and why we to restrict the designer to what is the width of the this placket, whether it can be the 1 inch, whether it can be 1.5 inch, whether it can be 1.2 inch. So the standards devices or standard folders available which can fold the fabric in 1 inch. If some designer says I'll require the 1.2 inch, 1.3 inch, whatever that is. So those standard parts are not available. So, but this type of the parts can be easily developed using the 3D printing. And when the lead time is very high, so there we are able to use this 3D printing technology as one of the industry 4.0 tool to get a solution. So how the process works, we have a metal part like this. This is a bottom hem folders. We did the reverse engineering. Then what are the features we extract? We did the modeling of the part. Then sometime we need to do topology optimization, and we have a 3D printed part with us. So then this is the part we just manufactured or 3D printed, and this is a hem folder. How it attained, like through the reverse engineering, we have a CAD model with us. CAD model on the the cloud data will able to build this CAD model. So I'm just demonstrating the CAD model has been building here. And after having the CAD model we need to convert into the STL file format. Then we need to do call the STL file format on the platform of the 3D printer where the slicing need to be done. So we just identify which orientation we need to print. So we'll fix that part. In that orientation, we'll do the slicing. We'll do the set the certain machine parameters also. What will be the infill and the certain other things which are a part of the process planning. Then we'll do the 3D printing of the part. Now the printing is done. We'll just remove the part from the build plate, and we'll just remove the what is support material. These are the process of the 3D printing, and now this part is ready to use in industry. That much thing is required. So, but before reaching to this stage, we did the number of the iteration about the design. Now this is the final. So now once it is fixed, it's easy to build the another part. So now it's working fine in the industry. Now another part is the pneumatic folder. Here you can see. Now we can see the loose thread while we are doing the stitching, specifically at the bottom hem and other places. So what the industry do, they don't have an actual solution with them. They make that Zugar type of the things here. You can see this is the additional part mounted on the pneumatic folder, and a copper pipe is coming from here. And this is attached to a compressed air, pneumatic air. And this, what it does, the air blows at this starting point, and the loose thread goes inside the fold. But and it takes some time. Like they need to develop these type of the part in house. There's no standard mechanism they do, so it's a couple of iteration required. And still they have a problem. It just blow the air at one point, but while the folding is happening, it fold across the seam, and still the whole surface area has not been covered. So just to overcome this problem, what we thought, we should have a channel inside, and there are the multiple stages also. What you said, the ground floor and the first floor type of the things. Here you can see in this diagram. So air opening has been made at the two places, down and then it goes across the surface on the top layer and the bottom layer. When we have a two fold here, that cannot be possible on this, where the 3D printing have an upper edge, and this type of the design is easy to manufacture using the 3D printing. And I'll show you this using this video here. Now this has been printed, and this is the blue pipe is the pneumatic compressed air is coming here, and this is the part, and you can see two fold is happening here. I think you're able to see, like, just wait for a while. And there will not be any loose part outside it. We'll try to go into the zoom here. Just one. So you can see there is no loose thread outside, because the air is flowing through the surface area, and that type of the complex part is not possible using the normal way of manufacturing. And along with the customization, we might have a ½ inch, 2 inch width length of the folding seam. We can have a 3/4 inch. So having those customized solution can't be possible. If we go for those parts, we have here you can see the no loose part is coming outside. So that we are able to develop, and these are being used into the industry. Sorry, what we have achieved here. So the cost of the initial part is 600, and 3D printed parts is 150 rupees. Instead of the 2 days, it's get be printed into 3 hours only. We have another example of the button folders. You can see that this is the button folder. Is also an expensive part. You can see the cost of the part is 2,500, and these pins have a very high wear and tear rate. So we did the reverse engineering. We did this part. We fixed up the part like this. Here we use the normal way of the manufacturing the part. We use the vernier caliber to get all the dimensions, and then did the modeling of the part. Then you can see this part has been putting on the Eiger platforms. Markforce is a 3D printing company, US company, and this has been we are doing the slicing here, the whole process which we just shown here. So then 3D printing is done, and some post processing need to be done once the part is print. So these are the low cost solution. Now you can see here, instead of those pins, we built this part, and just to get the actual dimension where these pins are need to become, we'll put the actual button on the other side, and we'll use the adhesive, and these pins come out from that side. And this part I'll show you how it has been put into this automatic, but this is doing the post processing or assembling of the various parts, pins and the buttons. It is very smartly designed, so whenever the button size different, so we just build on it. So now it has been put on the machine. So the video is fast. I'll just stopping it here. From this side, you will see a moving hand will come that will fix the button just below this, and where this button will be fixed on this garment. That comes very fast. Yeah, this is coming here. So these type of the solution using the industry 4.0 we're trying to give to the industry. And another case studies are also there where the wear tear happen. So instead of the single part assembly, we make the assembly. So we redesigned it. Now it's a 2-part assembly. Wherever the wear tear happens, that part can be replaced easily. This type of the cams has been designed. And there are the other parts which are designed. You can see this type of the complex part or the fusion folder. This is a single part, and this can be very easily printed using in one go. Otherwise, these are very difficult to have these type of the parts. Now the fourth one is intelligent production monitoring system. Now this can be just like of any other production monitoring system on any manufacturing industry. And there are 2 types of the requirement in a shop floor. One is the production data. What was the plan for the day, and what was the plan, and what was the actual happen. Those type of the reports need to be generated on the shop floor. What is the machine productivity? We have the various machines. What is the individual productivity? These type of the information that required to be collected, and there are the various means and modes through which the data has been collected. The earlier time, what the industry do, they have a logbook type of the system. When one operator done with certain number of the parts, so they write over there. Later we have an RFID type of the systems. So whenever the bundle done, they just tag that, they just show that to the scanner, barcode scanner. So it sends that the 10 parts has been done. So those data has been captured. And what the industrial engineering people need, what is the predicted efficiency for the day, where the bottlenecking happening, as this is the garment industry is the assembling line manufacturing system. So if one operator is not doing as per the time allocated to him, those also done on the scientific base, and then the bottlenecking started happening at that place only, and the operator after him will keep idle for some times, and the operator before him also do the overproduction. So because of the the weak section in the one of the operation will not able to attain the desired productivity in the daytime. But that is the one of the question or the challenge. But when bottleneck is happening, it generally, because we don't have a real-time data available, so whenever the bottlenecking already happened, we are able to understand that bottlenecking happened. Then we'll put another operator to bifurcate that work in two different operators just to remove that bottlenecking. So that those were the processes. Now we need to know in advance where the bottlenecking is about to happen, and there is no mechanism till time, and whatever the mechanism industry is using the RFID solution or some BARTech type IoT enabled machines, those through the understanding of our in this domain, we identify those not the foolproof solution. Still, there the lot more scope is required to have a real-time scenarios, and what the basic unit they uses to do whole the calculation, that is not also very good, like how that is happening now. So this is one of the solution which industry presently is using. They have an overhead material handling system. The one famous company is the ATAL. So the fabric goes from one place to another place in between the stitches. So that is called the WIP, one operation to another operation. And whenever operator start doing the operation, like he's attaching the pocket or either he's attaching the collar, the machine just started a tag and just time he notes what time he in totality taken to complete that operation and what was the actual time allocated to. Now this time doesn't talk about, suppose he just tagged the his garment while he's doing the operation, then he keep idle for some time. He's not performing the task on the sewing machine in between. And when he again tag it, so the machine just understands what is the time elapsed in between. So it will not able to identify in this whole time, for example, it's 2 minutes, how many times was he took to do the stitching actually. He might be handling the fabric, he might be doing some another task, the whole time accounted for the operation only. That is not the true picture. The present scenarios, the present available solution just use this basic unit to give the entire solution. So that's why they don't have a good efficiency. Now, RFID also works on the similar work. So we have a bundle type of the system. So 10 pieces are being bundled together and they have been allocated to one operator. And when he start, he just show the bundle tag to the RFID scanner. So it's understand that 10 operations are been marked, given to that seat, that operator. And once he finish, he again shows the tag and the system understands the 10 operations has been done and that has been moved to the next level. So again, the system is not able to capture what is the real working time, machine time happened for stitching the individual garment or what the operation he was performing at this time. So that was the in technology advance, and we have nowadays the IoT enabled sewing machines. They have whenever an operation completes, the thread need to be break. So they use that time. What is the time elapsed in between the two thread cutting? So they use that basic unit to evaluate the overall production monitoring system. But none of this operation system is able to identify or capture the time what is the machine running time. So for that we just analyze what is the the capabilities of the present system, whether we have a scope of implementing or developing a new system which is capable to give the better results, whatever the present solution, whether they are intelligent enough to predict in the upcoming bottleneck which line it is going to become, when it is going to come. So we compare the present system. So RFID and the overall material handling system and the IoT machines. So those all are the sensor based, one or another type of them. Their accuracy is 70 to 80%. This IoT have a comparatively high 80 to 85, but still not 100% or close to 95. The cost is high, medium, high. The RFID is the cheaper one. Whether they are integrated with the existing non-IoT enabled sewing machines, yes, these two are capable, but this IoT enabled machines are not been put into the existing non-IoT enabled machines. AI enabled system, no, none of them is the AI enabled system. They are not giving you the prediction for the upcoming bottlenecks and the day-to-day production data. And whether they are capable to tell you what is the needle running time, which is the actual value addition time to your garment. Whenever needle runs, means you're doing some performance on the garment. So none of system is not able to give that. And I'm talking about the RFID and this overhead material handling system. IoT talks about that. Average pick and place and dispose time, other than the needle running time, I have to need to hold the fabric, put it some another place. Whether the systems are capable to identify those times, no, none of the system is capable. Whenever rework happen, whether they are able to identify whether rework happened or they are doing the actual process. When they have a quality issue, what happened? The QC quality checker send the garment again to the operator. Now this was the pocket has not been attached, so he's just remove some of the thread, sewing thread, that is called the ripping process, and do the stitching again, just to attain the desired quality. So my systems are not capable enough to identify whether it's a normal production or whether it's a rework is happening. So that is the lacuna. Production progress monitoring system, yeah, they are giving, but base unit is not good enough to give you the 100% accuracy. Bottleneck identification, they're able to know where the bottlenecking is happening, but they're not able to predict where it is going to happen. So what we thought of, just to have a solution which we developed for our iSmart system. So we use the similar encoder and put on the machine, and it is capable to give the data to a router, and through and cloud data, we can do the analytics here. And what type of the system it will be? So we have this black box can be mounted, which is Wi-Fi enabled and Bluetooth enabled, and it gives the machine data. It understands when it gives you the data when needle is running, when needle is not running, and this whole all the machines have been mounted. They are through the gateway, IoT gateway. The data will goes on the cloud, and the system is capable to identify the basic needle running unit times, because it understands when needle is running. It only gives the data when needle is running. Now, what the logic behind it, how it calculates, I'll just give you in one slide here. Now here you can see the data we are capturing for one type of the operation here. So these are all similar patterns. Whenever their rework happen or non-productive happen, you can see this data, this type of the data capturing is difficult. So we developed the algorithm which is capable to identify the similar patterns, and where the dissimilar pattern occurs, it will identify where exactly it is, and also able to identify how many identical cycles has been done on the same machine, what type of the operation it is. If we are doing the collar stitching, so different type of the patterns will there, it will able to identify those things. So the system can able to tell you that the out of these 31 cycles, these 30 are the useful cycles and operation happen, and this is the one non-productivity cycle, and that happened at this time frame. On the x-axis we have a time series. So just to give you an idea how fairly it works, so it's the start 0 time, end data time is 2136 seconds. Total number of identical cycles are 30, and what is the noise? We term it as a noise. It's a non-productive time. So that's the way. So this is again in the project, which is the proof of the concept has been done. So we are working into the domain of doing the commercialization solution. So what advantage we can have using this? So we are able to identify the needle running time, how much time needle is being run. We are able to identify the pick and place and dispose of time. We can able to segregate wherever rework happen. So we'll able to identify this here the rework happen. Production progress monitoring system is there. Bottleneck identification is there. AI based prediction can be done using this data. Accuracy is up to 99%. Real-time data updation happens because it always goes on the cloud. We are planning to make the dashboarding which shows you what is happening on the shop floor. Operator evaluation can also be done, whether he's performing good or bad, what is his productivity in first hour, what is his productivity in second hour. So that also been calculated. And it also works as a virtual time study engineer. So you some PMTS or what you say the industrial engineer need not to stand on his hand and just to measure or observe what exactly he's doing. This can be done virtually. So operator is free to work. This what you say the black box is mounted on the machine. It gives the data, and on the cloud we'll able to understand what type of the operation is doing, what is his overall time, whether he's stopping in between the operation or not, using that pattern recognition. So these are the advantages. So this is the full presentation of the 4 different type of the solution we are developing in the industry 4.0.